Welcome to our tutorial on Not Your Grandpa's SSD, the era of co-designed storage devices. So SSDs are here and they're here to stay. 10 years ago, we were discussing SSDs, solid-state drives, as replacement for hard disk drives. Today, we realize that flash memory actually provides better cost performance than RAM for database systems. So for our community, there are basically two issues. First, how to choose SSDs for a given workload. This is not trivial. The design space is large, so we'll explain how this design space is organized, how it's evolving. And now it's also possible to design SSDs which are tailored for the needs of a given workload. It's made possible by the evolution of SSDs and the introduction of computation together with storage within SSDs. And what is possible now is the co-design of a database system together with the SSD. And this is an exciting research challenge, which will require expertise from many different fields. This tutorial is our attempt at engaging the database community. So why should you care? Either you're using SSDs for your experiments, and you need to understand how to choose an SSD or how your choice of an SSD actually impacts your performance results. Or you're designing SSD-based or flash-based database systems, and then a deep understanding of the storage protocols and devices is necessary to design your system. And we hope that many of you are willing to be convinced that co-designing databases and SSDs is worth your time and energy. So we'll talk about terminology, we'll talk about related work, existing work, and open issues in the area. So we could talk for hours about the topic. We have an hour and a half, so this is not a complete coverage of the domain. We present a curated survey and refer to resources, especially in the associated paper. We are biased. Alberto and I have been working in the area for some time, and we're pushing for the co-design of databases and SSDs. So we emphasize what we see as the main takeaways throughout this tutorial. We also realize that in this tutorial, we will not settle current open questions. Our goal is to engage the communities and delineate areas of further study. So I'm Philippe, and I will let Alberto take over for the rest of the introduction.
Hi, and I'm Alberto. Thank you for the opportunity of being here. Let's start by looking at a historical perspective of how SSDs evolved. Flash was invented in 1980, but it took almost a decade for the first SSD to be introduced in the market. The idea of this first generation of SSDs was all about compatibility, being a drop-in replacement for hard disk drives. Not much happened in terms of interfaces, but that helped the SSDs catch on. The next big evolution happened with diversification. SSDs took over the stable storage market because in a number of metrics, they are better than the other alternatives. And they started becoming faster and faster. Along came a protocol that we're going to be talking about a lot of direct attachment storage called NVMe. And this is more or less the phase that we see now. What we're arguing here is that we may be looking at a start of a next phase in which we move away from this drop-in replacement role and into SSDs becoming a more active part of a computing architecture. First of all, the NVMe is widespread and allows a number of evolution mechanisms for us to explore. Second is we're seeing more and more possibilities for increasing control of storage from the application, and we're seeing opening opportunities for co-designing these devices as well. Throughout the tutorial, we're going to be talking about two big perspectives, the architectural perspective and the programmer's perspective. On the architectural perspective, we're going to be discussing how data moves between application and devices and how the control is divided between those two. You're going to see images like this, and we're going to talk about them later, representing applications, generating workloads, coupling with devices. And you're going to see figures like this that you're probably more used to that depicts layers of the system. When we talk about the programmer's perspective, what we're going to be doing is basically blowing up, investigating what happens inside of each of these boxes, what kind of abstractions are used for the system to, different components of the system to communicate with one another. You're going to be seeing those images again soon enough. Don't worry about understanding them just now. If we had to summarize the talk in one slide, this would be it. And this would be the 3 bullet points. The grandpa approach has been writing software that adapts to historical limitations of the SSD. Don't touch the SSD much, make the adaptation come from the software side. The second point is we can start making adaptations in these devices using what we call external and internal interface. External interfaces are used to send commands that are semantically richer to the device, describing in more detail how we want certain operations to be executed. And internal interfaces are mechanisms that allow us to take control of these executions. We're going to be talking a lot about those two. And lastly, we can use those concepts to devise new devices that are going to be doing their fair share of adapting to the application. We're not talking about one particular class of adapting devices. In fact, we think that there are several different categories, new and old. For instance, we can have devices that take configuration parameters from the application and behave in a certain way. The NVMe protocol, which we're going to be talking about here, allows for this kind of thing. We think that computational devices are going to play an important role as well, and these are far from new. There has been plenty capable teams working on these devices for quite a while now. There are also teams working on devices that have been programmed to behave in a different way to fit a particular workload in a tighter fashion. What we think is there is an unexplored category here of truly co-designed devices where we design both database storage systems and storage devices together and have them interact in a tighter fashion. A couple of practical comments. We are going to divide our talk in two. This would be the first half, talking about the internal and external interfaces, and this would be the second half, talking about computational and programmable devices, and then a bunch of techniques and mechanisms to develop them. Some of the material is going to be offline because of the limitations in duration of this tutorial. We are going to have references on the online versions of the slides. This helps us keep the slides here lighter, not so much polluted with their references. We have tons of them. We're going to be doing a break at 45 minutes, at which time we can open up for discussions and questions, but we're going to be available throughout the conferences if you didn't get a chance to ask your question then. And now we're going to talk about internal interfaces. This is part 2 of our tutorial. Let's begin our exploration by looking at NAND flash and the internal architectures of SSDs. NAND flash memories have certain peculiarities. For instance, they do not support updates in place. Memory needs to be erased before it can be written to. The read and write operations do not take the same amount of time. SSDs are built to support these peculiarities and have gone to be quite sophisticated systems. They have a number of internal components, and each of these components' actions can help or hinder performance. The components interact with one another through internal interfaces that are not visible to applications. Through the interfaces, the SSD creates what we call a data path that carries data between user application and flash. Understanding the data path allows us to create a more systematic way to analyze an SSD performance and its design trade-offs. Flash memory sits at one end of this data path. It is organized hierarchically in the device. The small unit is a page, as I show here. A block groups together a number of pages, and a LUN brings together a number of blocks. The LUN is the smallest functional unit that can independently service a read or a write, and there can be several LUNs per package. As a consequence, SSDs are highly parallel devices. They can be servicing several reads and writes at the same time. Data is not moved directly into a page. It is first put in a staging area called a page register, or sometimes a data register. In some newer devices, there are other staging areas called cache registers, but let's make things simple for us for now. The transfer and actual operation can be interleaved in different ways, which would translate in different latency and throughput. Incidentally, we'll comment on part 3 how we can expose the latency and throughput trade-off and potentially even influence it. A flash package is a physical chip that contains the LUNs. There's a standards body called ONFI that determines the physical and electrical interfaces for the packages. The signals are divided in data signals and control signals. This means that someone inside the SSD but outside the flash package is supposed to be communicating commands and getting data in and out of the package through the ONFI signals. We call this entity the flash controller. We were talking in the previous slide about transferring data in and out of the page register. Well, that's one ONFI command. We're also talking about transferring data from the register into the flash page. That is another command. So the flash controller orchestrates the movement through agreed upon protocols. Let's see one example of how the flash controller interacts with the package. What I'm showing here on the left side is called a waveform. You can see the control signals over here and the data signals over here. And I promise this is the lowest level detail we're going to see. Don't worry too much about understanding every single aspect of it. I just want us to get the gist of it and how the flash controller is supposed to talk to different LUNs. So the control signals are basically going to be used to say, hey, I want to talk to this particular LUN or to this particular LUN. And then they're going to provide the timing for the operations to happen. And then once this timing aligns on both sides, then data could be shipped into the page register, and in a further command can be put into a destination page. Now notice that these operations are going to be scheduled sequentially, and there may be some latency between the first and the second operations. And here's an example of this latency decisions. Imagine that we want to do 3 reads, each against a different LUN. We're calling them chips here. The read is the opposite of the write, which means that you have to bring the contents from a page into the page register first, so this takes a little bit of time, and then you have to transfer the contents of the page register out of the LUN. If we want to have a continuous flow of data this way, this is how we would schedule the operations. There's an entity inside the SSD that's called the channel controller that is responsible for coordinating among several LUNs. The way they are usually connected is each individual LUN has control signals independent of one another, but they all share the same data bus. This way, the channel controller can hide the latency between individual operations, and it can aggregate the throughput of several LUNs together. Another component on the data path is the ECC engine. Flash memory presents a high rate of error, and without an ECC engine, data cannot be consumed nor be stored. The flash packages have some mechanisms for lowering the error rates, but they're still not sufficient. And you need to pair the channel controller with an external ECC engine. Let's fast forward our task of building the data path, and let's add the 2 missing components. The host interface controller is responsible for implementing the NVMe protocol and to transfer data and commands in and out of the device. We'll talk about NVMe in more detail in part 3. Once the data is in the device, but before we can send it to the storage controller, which is a combination of the components that we've seen before, we have a component that's called the firmware. We call it this way because the firmware can be implemented in software, and it actually is in one of the devices that we're going to discuss later. The firmware is where the FTL is, but it also carries additional components. It can control the DMA that the host interface controller implements, and it can determine the low-level scheduling that the storage controller is going to utilize. In other words, the firmware can be the brains of the operation. Now that we've seen the components that form the data path, let's take a look at how an NVMe write command is handled. The host interface controller fetches the command from the host memory, and let's assume it's a write and its size is 1 page. It transferred the new contents into a data buffer in the firmware. The FTL picks a page for the contents by doing page mapping, and this determines which channel should perform the operation. But there could be several pending operations for that channel, so we use a low-level scheduler to determine in which order to issue them. When it comes the command's time, the flash controller transfers the data into the page register for the assigned LUN, and it finally issues a program operation against the designated page. We're glossing over a significant amount of details here in the interest of time, but the important aspect is this. There are several decisions taken along the way. They reflect the policies that the device implements. For instance, a caching policy for when we need to get rid of something in the buffer to make space for something else coming in, as well as a data placement policy, a channel utilization policy, a policy that balances the strength of the ECC and the longevity of the device, and these are only a few examples. In a generic device, this policy should be as generic as possible. If our utilization of the device is compatible with the policies, we get good performance. But the problem is that's not always the case. Now, we're not talking about performance issues because an operation is blocked on garbage collection. We can have a workload that's made up of just read operations. There's no block erasers, and still have subpar response times. Here are a few reasons why. One, we're sending more than one workload into the device, and the workloads are competing with one another. Second, the pages that we're reading were written in the device in such positions that create hotspots. They don't allow parallel read enough. And there could be a whole other number of limitations because we're using the device in specific ways that do not match the generic policies that are embedded in the device. Now the question is, if we understand our workloads well, and we're sending a few well-understood workloads towards the device, why can't we tune these policies to serve these workloads better? Let's pause a bit and talk about database workloads. What are they? It turns out that there are not too many. The databases have transaction log, checkpoints, workloads that are generated by the buffer manager activity, data loading, external sort, spills from other operators, online query scans, and a few other. We know these workloads. We know how to characterize these workloads because we control them. Take for instance the transaction log and the checkpoint. They're both sequential in nature. They both are predominantly write, but for recovery. The queue depth, the number of outstanding operations, is different between them. Transaction log is not going to issue a new operation if the previous one hasn't finished. The checkpoint can be done in parallel and have many operations in flight. The size of the operations differ as well. Transaction log usually writes small pages. The checkpoint can be writing multiple pages at the same time. And there are other characteristics that could be interesting. But now that we define these characteristics about the workload, we can reason about them. For instance, the checkpoint can overwhelm by its sheer size a transaction log workload if a proper scheduling policy is not in place. And these policies are what we're going to turn our attention to now. The claim here is that there are certain areas of the SSD, internal areas of the SSD, that deserve interfaces so that we can swap or configure policies more easily. Let us go through them. Caching in the data buffer is one of the areas that deserves an interface. The data buffer is finite, and without having any information about the workload, we're going to implement an LRU to pick victim pages. But different pages may have different utilities for the databases, so we should be considering that instead of just measuring the frequency of access. Data placement is a second area that deserves an interface. Once again, without any information, we're just going to pick the next available one on a round-robin fashion. There's severe problems that may arise from that. For instance, we may be mixing pages with different lifespans, which makes GC work much harder. We should instead consider how the pages that we're writing are going to be read and then decide on a position. A generic channel utilization policy would try to hide latency and maximize channel bandwidth. This may lead to lack of fairness if workloads of different sizes are mixed. We saw that a couple of slides ago between the transaction log and the checkpoint. But we're not arguing for fairness. In fact, we want a controlled unfairness because some workloads are more important than others. We need to be able to express these relationships through an interface. ECC contributes to the latency of every operation, and it takes a lot of area to implement in a device. Certain applications may tolerate a lesser degree of error control. For instance, bit flips in large images. It would be interesting to be able to calibrate how much SEC we're applying to which kind of data. The point about having internal interfaces is that from an architect's point of view, we shouldn't stop designing the database at the bottom of the storage manager. We can continue designing the database relying on behavior that we can configure inside an SSD. From the programmer's perspective, it pays off designing and implementing I/O workloads that can be easily characterizable. Granted, the interfaces that we discuss here are very low level, but we will see in the next part that there are ways to hide these policies inside the SSD under higher level abstractions. A database system would use those abstractions to pass information on how the policy should behave. Thank you.
We're now going to cover external interfaces. External interfaces define how SSDs are exposed to the rest of the system. This is an area which has been very stable for many years and which is now undergoing a radical evolution. We could spend hours discussing the evolution of external SSD interfaces. Here we're going to give an overview of the key abstractions and mechanisms. We decided to cover only existing technologies. If you want to go deeper on any issue or if you want to discuss the future of external interfaces, please ask us any questions. So for decades in Unix systems, applications map data structures onto files on top of the block device interface. This is now legacy, but it's a very important point of departure for our presentation. So if we go bottom up, hard disk drives first and then SSDs expose storage as a block device. The block device interface abstracts storage as a linear array of fixed size blocks. Each block has a logical block address, LBA, and it's a typical memory abstraction, so read and write operations. On top of that, POSIX IOs abstract storage as a collection of files. The operating system contains inode data structures that map each file onto a collection of blocks. The original POSIX specification defined synchronous operations, so read and write, so very simple and deep abstraction. Also, by default, buffering was used to avoid IOs as much as possible. And applications map their data structures and their workload onto files and the memory abstraction. Part of the legacy component, which is very important to remember, is that an ecosystem of tools and commands has been defined to make it easy to organize and manipulate files. The block device interface and POSIX were defined for hard disk drives. So now we've transitioned from HDDs to SSDs. SSDs are orders of magnitude faster than HDDs. Now, if I/O performance doesn't matter, then you can stick with a POSIX file with buffered I/O on top of a block device interface. If I/O performance is crucial, which is the case for database system, we used to define a storage manager with custom buffer management with direct access to the devices on top of a block device abstraction. This has been the case for decades. Now with SSDs and the definition of new abstractions, we can and we have to go beyond POSIX and beyond blocks. This evolution is led by the evolution of the NVMe standard. So we're going to go into some details about the evolution of abstractions beyond POSIX and blocks. Just a point, I'm talking about SSDs, but it's really important to recognize, as we've discussed in part 2, that SSDs are not a uniform class of devices. There's a continuum from latency optimized disks, like based on ZLAN flash, to archival disks. So what's wrong with POSIX? POSIX is a textbook example of a deep module. It has remained stable for decades, but now it's in the way of performance. It doesn't allow applications to control data placement or I/O scheduling, and the many layers which are necessary to implement the POSIX abstraction create redundancy and missed optimization opportunities. So we need a streamlined I/O path. How about blocks? The block device interface hides a lot of complexity. And it was instrumental for the adoption of SSDs, that SSDs respected the same interface as hard disk drives. Now that SSDs have been adopted, the block device interface is in the way of performance, mainly because it hides the intrinsic parallelism which exists inside SSDs, and also because it requires a complex firmware to handle the idiosyncrasies of flash, and this firmware is in the way of performance. So we need SSDs interface that expose parallelisms, and we need to align the storage interface with the internal SSD characteristics and with the external needs of applications. So while with POSIX and blocks, it was very comfortable, we had very high level of abstractions. Now we need to go for a streamlined I/O path that exploits SSD parallelism, and this requires a deep understanding across all layers. So let's start with the PCIe. So that's the interconnect. So again, we need to understand at least a bit about the characteristics of PCIe if we're a system designer or even an experimenter. So PCIe is a network protocol. So we have basically a transaction layer based on requests and responses on top of a data link layer, which is again on top of physical connections organized as a collection of lanes. Each lane is a pair of unidirectional serial point-to-point connections. That's really important. So PCIe is not a bus, it's a collection of point-to-point connections. The PCIe fabric is organized as a tree with a root complex and multiple endpoints connected directly or via a switch. So the root complex of the PCIe tree is either the host or a PCIe switch. Each device is associated to a memory mapped region of the host address space. This memory mapped region is defined through a base address register bar. And the theoretical bandwidth of PCIe is comparable to RAM's theoretical bandwidth. It's doubling with every generation. So we are, in terms of standard, we're now at generation 6. In terms of products available, we are generation 4 to 5. So PCIe is important, but NVMe is absolutely crucial. So NVMe is the application level protocol on top of PCIe. It was first specified in 2011 by a consortium led by Intel. The latest version of the standard, NVMe 2.0, was released a few days ago. So NVMe is purely asynchronous, so it relies on pairs of submission and completion queues. So here on the diagram, we see a host communicating with a controller. We have administration commands and I/O commands, and for each, there are pairs of completion and submission queues. On a core, you can have a set of submission queues associated with a single completion queues. Queues are located in memory mapped address space, either on the host or on the device. So the host places a command on the submission queue and rings a doorbell, so a specific register, to tell the controller that a submission entry is available. So the controller fetches the command from the submission queue and executes the command. The execution of a command might result in a direct memory access, so DMA. So it's the controller, which is the DMA master, and decides to read or write the host memory. Once the controller is done executing a command, it puts a completion entry in the completion queue and generates an interrupt. The host processes the interrupt. Typically, the core that issued the submission entry also processes the interrupt and processes the completion entry. Once this is done, the host rings another doorbell, so another register, to tell the controller that the IO has completed. So this is the core, the basics of NVMe IO. So NVMe was defined for PCIe and was later extended to other types of fabrics. So with PCIe, that's the situation we've just seen, where submission and completion queues are in memory mapped address space, and DMAs are used to transfer data. On Fabric, the NVMe commands are represented in the message-based systems using so-called capsules, and data are transferred either using those capsules or messages on top of TCP and shared memory on top of RDMA. So in NVMe, using shared memory, the queues and data are usually placed on the host, that's the host memory buffer, but it's also possible to place them on a device using a controller memory buffer. So controller memory buffer is a CMB, it's part of a device memory, which is exposed through PCIe, and so it's available to the host, which can place either queues or data for optimization purposes. It's also available to other NVMe devices. And so through CMB, it's possible to consider peer-to-peer communications. There's also the notion of a persistent memory region made available through PCIe. So we've talked about the I/O mechanisms in NVMe based on submission completion queues. Let's now talk about the abstractions. And the abstractions are based on two key concepts, the notion of namespace and the notion of command set. So a namespace is a quantity of non-volatile memory, so storage, that may be accessed from the host or from another device. So each namespace has an ID, a size, a capacity, and to a namespace is associated a command set. And so in NVMe, there are basically administration command sets, Fabrics command sets, and most importantly for us, I/O command sets. And there are basically three I/O command sets defined in NVMe 2.0. NVM, which is basically the traditional block device abstractions, so read and write. Then ZNS, the zone namespace command set, and then the key value command set. So let's take a deeper look on those command sets. So the admin command set is about device identification and introspection, as well as queue management. The NVM IO command set is the traditional block device abstraction, where the namespace is a collection of logical blocks, and we have read and write commands. What's new and a departure from the traditional block abstraction are the zone namespace, ZNS, and the key value command set. So in ZNS, the namespace is partitioned into zones, and each zone is a collection of logical block addresses. So that's an attempt at exposing SSD parallels. In addition, some constraints are defined that have to be respected. So logical blocks must be written sequentially within a zone, and zones must be reset before they're written. Usually, it's the host's responsibility to manage a write pointer within each zone to make sure that those constraints are satisfied. The standard also defines the append command, which lets the SSD actually manage the write pointers. So with the append command, the host can issue a set of append commands concurrently without synchronizing any write pointers. So ZNS is relatively new. It was introduced last year. It's now an integral part of the NVMe 2.0 standard. What's interesting is that we cannot buy ZNS drives. We cannot even experiment with samples. Vendors are tightly collaborating with hyperscalers to develop ZNS drives and that are well suited for the workloads of specific vendors. So we cannot experiment with ZNS right now. there's hope that if DNS is successful, then in the not so distant future we'll be able to have access to DNS drives, but that's not the case right now. Another point that needs to be made is that DNS is not meant as a replacement for NVM. So there's still room for the traditional block device interface. And the question is basically what kind of workload is well suited for DNS drives. So hopefully we'll be able to study this question at some point. The key value comment set is associated with the namespace organized as a collection of key value pairs of variable sizes. The maximum key size is 16 bytes. And the commands associated with the key and values are store, retrieve, list exist, and delete. As far as we know, there's no support for key value in the Linux NVMe driver. There's a support in some user space NVMe drivers. So interestingly, there's a mechanism in NVMe to support cross-layer optimization. It's called directives. It makes it possible for the host to send information to the SSD in connection with a given operation. For now, the support is pretty limited. It's only the NVMe IO command set, and it's only support for writes and one directive, the so-called stream. Streams make it possible for the host to say that some writes belong together within a given stream. And an SSD that received such IOs can place data based on the stream they belong to. That's very advantageous for garbage collection or if data is often accessed together. There's support for directives in SPDK and implicit support in the Linux file system through the lifetime hits. So let's now move from the host to control interface to the interface between applications and the operating system. And so let's first start with the now legacy IO frameworks in Linux. So the original POSIX interface was based on synchronous commands available through the system library. Many of us still reason in terms of those synchronous interfaces actually. So read and write is beautiful, but it's dated. With asynchronous devices, it's been necessary to introduce asynchronous IOs in the mid-2000s. And there are basically two flavors in Linux, AIO and libaio. I don't want to spend too much time on it. AIO is basically a user space simulation of asynchronous IOs that rely on synchronous worker threads. And libaio is an actual asynchronous interface, but which has many limitations. So asynchronous IOs were always a bit of a mess in Linux, and to fix that, Jens Saxbo introduced IOUring in 2019. So IOUring is now mature. It's based on pairs of submission and completion queues that are shared between user space and kernel space. And system calls are available for setting up those queues, registering memory that is referenced in the submission queues, and initiating and completing a number of asynchronous IOs. So by default, and what's key here is that IOUring requires a single system call for multiple IO submissions and completion. It's also possible to set up a queue pair with a given flag so that IOUring starts a kernel thread that polls the shared submission queue for entries. And that's basically trading increased CPU utilization for lower IO latency. So IOUring is pretty complex, and that complexity is exposed to applications. To hide some of those complexity, libaio-ring has been defined. So it defines a range of helper functions for setting up the queues, manipulating the buffers, and generating the submission queue entries with that context. IOUring is again maturing fast, and so it can be used with any file system, with buffered or unbuffered IOs. It recently added support for submitting IO CTLs. So IOUring is now the modern IO framework in Linux. So now as a programmer, you have a range of different choices in terms of IO framework. So you can bypass the buffer cache. That's what database people have done for many years using IO Direct. It's possible to bypass the file system, still using the block layer. So opening a device file directly as basically a raw device. And the block layer provides different mechanisms to deal with completion. In particular, continuous polling, which makes it possible to dedicate a kernel thread to polling the completion queues. So it's another way of trading increased CPU utilization for lower I/O latency. It's also possible to bypass the block layer using ioctls to communicate between an application and the NVMe driver using synchronous commands. So that's one of the limitations of using ioctls. And finally, it's possible to fully bypass the kernel using user space NVMe driver. The most prominent framework is SPDK, which maps PCIe bars directly into the application process. And that makes zero copy possible. So SPDK trades increased performance for, and gives up the protection from the operating system. Also, SPDK exposes basically some of the limitations of the underlying SSD directly to the application. There's no operating system to mediate. So SPDK defines a new C API, so NVMe.h for block devices, and NVMe ZNS.h for ZNS drives. So SPDK incorporates the ZNS command set from NVMe. And it's the application's responsibility to enforce the single thread, that the single thread submits I/O and that this thread polls for completion. So in summary, if we compare the two modern I/O frameworks, SPDK and IOU-Ring, SPDK favors performance. So it's possible to have zero copy, and by default, SPDK trades high CPU utilization for lower I/O latency. On the other hand, SPDK exposes applications to the limitations of PCIe and NVMe in terms of number of queues, number of entries per queues, the size of the buffer regions, and the fact that a single thread must handle submissions and completion. IOU-Ring traverses multiple software layers. It requires a copy between software and hardware queues within the block layer, and it's also very complex. On the other hand, IOU-Ring isolates applications from the limitations of PCIe and NVMe. It supports a range of targets from raw device, files, and even ioctls, and different tuning options, and performance as well. I mean, it's a single system call for a collection of IOs. But SPDK and IOU-Ring are both performance. They're both complex as well. The question is whether it's reasonable for application developers to have to make a choice between SPDK and IOU-Ring. And to address this issue, the people at Samsung in Copenhagen have defined XNVMe, which is a user space library that abstracts SPDK and IOU-Ring and provides a clean abstraction to application developers. So it's a means to design portable, simple, yet efficient NVMe-based software. And what's interesting in XNVMe is it recognizes the key position of NVMe. So some concluding remarks about external interfaces. So first, NVMe is central in the storage stack. NVMe was defined for transport-based networks, so PCIe or Fabric. And now there's a new generation of interconnect being defined. So they're memory-centric, CXL or Gen Z. What is the role of NVMe in those memory-centric interconnects? That's an issue we've chosen not to address in the tutorial, but we'll be very happy to discuss this issue if you're interested. Also, an important point is that there's a set of different abstractions, but there's really no sweet spot for database workloads. So with the traditional block device abstraction, the limitations are well documented. With ZNS, you can choose which zone you put data in, but there's no impact on placement or scheduling at the physical level. With key values, there's no caching on the host, which might be a problem. With Open Channel, you have a lot of on the host can make a lot of decisions, but without any understanding of what's going on inside the device. So you can do I/O scheduling from the host, but without any information on the state of the channels. So the question is whether computational storage is a way to address this issue and to actually define an external SSD interface, which is well suited for database workloads. From a programmer's perspective, we mentioned directives in NVMe, which are a generic mechanism for cross-layer communication, which is underused in the standard, and that could be interesting going forward. And the final point is that those new abstractions and mechanisms in terms of external SSD interface, they motivate a new design, a redesign of the database systems storage managers And we believe that this is an opportunity for involving SSDs and to have SSDs co-designed together with these new database storage managers.